Okay, so we're going to be generating some fractals today. So basically these are infinitely complex mathematical constructions. There's certain things that sort of exist in nature which have similarities. We won't go into that. But I'll just mention, so this is our zoom level. So we're at the power of 10 to the 54. Zoom along to about 70. So if you took that frame, and so the smallest thing that can possibly be measured is Planck length, which we can't actually measure, which is 10 to the minus 35 meters. Largest thing in the universe itself, is about 10 to the 35 meters, which is a range of 10 to the 70. So if we went back to 10 to the, zooming in 10 to the 70, if we scale that down so that it was Planck length, to actually draw the entire fractal from that scale would take the entire universe. So they're pretty hugely sort of complicated things, but they're actually quite easy to generate. But before we talk about generating fractals, I want to talk about sort of the state of computing. So in sort of 1977, 2 years after I was born, the Cray one, the Cray supercomputer, you could go and buy one off the shelf, so to speak, for $8 million, which is probably about $150 million in today's dollars. The thing, 5.5 tons, it ran a whopping 80 megahertz. And it's freon cooled, basically immersed in liquid freon, and it did a whopping 0.16 gigaflops. And gigaflops are billion floating point operations per second. So a few years later, we get to 1985, skipping ahead a bit, the Cray 2 supercomputer. There was a Cray in between called the Cray XMP, which, does anyone remember The Last Starfighter, the movie? Okay, that was the computer generated scenes on that were rendered on a Cray XMP. So, and it took weeks and weeks. But anyway, Cray 2, $16 million. So, it's probably a comparable price if you take inflation into account. Again, the whole thing is basically immersed in fluorinert, which is a 3N product. If you've seen The Abyss, where they have breathing the oxygenated liquid, that was a variation of fluorinert. So you can oxygenate it, and you can actually breathe it. So not that you probably want to do that in this case. It had 2 gig of RAM, 1.5 gigaflops. So okay. So moving on, going on about jumping about 5 years ahead each time. So we're up to 400 megahertz, 4 cores, 25 million, 22 gigaflops. Getting slightly more interesting. Okay, we're up to 386 gigaflops, 2048 cores. So this is actually no, it's still not very exciting. I was going to say, okay, the Earth Simulator. It's quite a big computer, $500 million to build. So the Cray supercomputers, you can actually go and buy one if you wanted to. This is a one of a kind, 36 teraflops, 3 terabytes of RAM, 5,000 cores. You can read the numbers. They sound big, but again, this is where we actually start to get into what probably is still actually would be considered fast. So 131,000 PowerPC CPUs. So these things are basically racks of motherboards with a bunch of CPUs on them. So almost 50 terabytes of RAM, 700 megahertz, which is not particularly exciting. Okay, Fujitsu K. So the Japanese, they built lots of supercomputers. So we're up to $1.25 billion worth of hardware, and as you can see, there are lots and lots of yeah, 88,000 CPUs, which each with 8 cores, uses 12 megawatts of power. Exceeded 10 petaflops. So we've gone from gigaflops to teraflops to petaflops. So this is 1,000 trillion floating point operations. Oh well. Okay, and kind of the current reigning champion until the Chinese built their flip the switch on the next one. 93 petaflops. It's got basically 10 million cores. It's massive, and not inexpensive at over $250 million. And so, the first computer I had access to was my dad bought an 8 MHz 286. Had no floating point unit, so basically approximately 0 gigaflops. But the first computer I personally bought was a 4860 X250, 0.05 gigaflops. So it's sort of comparable to a Cray 1, which was 0.16. So this is 1/3 the speed of the Cray 1 supercomputer. My current computer is it's an i7 477K, 177 gigaflops. So that's actually quite significant in terms of some of the supercomputers we're looking at. And my phone here, 3 gigaflops. So this is approximately, I'm not actually sure exactly how much I can work it out, but that's quite a bit faster than the Cray 2 supercomputer, so 50% faster. But a lot of these, so we also have GPUs, which we're not going to look at today because you need to write stuff in CUDA and OpenCL and stuff like that to take advantage of the GPU. But the GPU on my phone can do is about the same speed as the my CPU. So, but you need to do some pretty specialized programming. But then you have to do some pretty specialized programming to operate a supercomputer as well. And my current graphics card is a 770 GTX. Does 3 teraflops. You can go to a computer store and buy 4 of these, and a motherboard that will take 4 of them. That'll get you up to 36 teraflops, which if we go back, will make you as powerful as that. So that costs $500 million. You can go and spend $10,000 now and get something that can do the same level of computation and sit on your desk rather than take up an entire floor in a building and probably require specialist cooling and that kind of stuff. So I just wanted to illustrate. So basically, my phone would be like the fastest computer in the world in about 1985-ish. So just to kind of put things in perspective, you could be using your phone to do, simulating the weather or furthering the Australian nuclear program by calculating nuclear interactions and stuff like that, or play Pokemon Go. So that's kind of just wanted to give you a feeling of how much things have changed over the last few years, and this is just the level of computing you've actually got access to, which is phenomenal. It really is truly insane. But anyway, so what we are going to do, I'm going to sit down, otherwise I'm going to be hunched over, because the rest of the presentation is mostly writing code. We're going to write a program to generate fractals, which are those pretty things, and actually I have a couple of slides. What are fractals? Except we're going to go from that one. Right in the show on screen. So there are fractals exist in nature. So like a cauliflower or something like that has this fractal patterns. We're going to generate them mathematically. They exhibit the self-similarity. So things on the large scale, if you zoom in, you see similar aspects of that reoccurring on ad infinitum. We're going to be doing the Mandelbrot set, which is sort of this fractal here, and we can see we're zooming in. And the big animation you saw earlier was a similar the same fractal. So it exists on a complex plane, so we have the imaginary numbers on this axis and real numbers. So complex numbers are used a lot in engineering and physics and stuff like that. Not so much so common in the real world, but basically they involve the square root of -1. Now, basically the formula for generating these fractals is you divide up your plane into a grid, each square being a pixel, and then you iterate a formula until either it exceeds a certain value or you reach the maximum number of iterations. Stuff inside the fractal, this area coded in black, actually requires an infinite number of iterations. So we're going to approximate infinity with about 1,000 in our case. And this is the formula. So we take our initial value, which is our pixel coordinates, we square it, and we add our original value for z, and we keep doing this, taking the new value for z, squaring it, adding the original value, until we reach this our bailout value. And then we colour the pixel depending on the number of iterations that was required to reach that. Probably sounds a bit obscure, but it will become a lot clearer when we write some code. So, and there's show me the code. So I'm going to create a new multi-device application, and we're going to need a sort of user interface. So I'm going to throw a T multi-view on there, and call it MV settings, although I'm not sure how many settings. We're going to do yes, throw a button, and I'll align that to top, and throw some margins in there. Okay, calculates, and another button. So we're going to make this multi-view slide in and out when we click on the button. And so on our multi-view, if I call this button settings, and we're going to make it look like a the classic hamburger menu. So we grab the style lookup and come down until we find one like that. Make it reasonably large. And on our multi-view, we change the master button property to our settings button. So that will allow us to slide in and out the panel. And the last thing I'm going to throw on there for now is an image, which is where we're going to draw our fractal. Align that to client. And call it IMG Mandel. And I'm also going to send that to back because it makes our button, so we can click on the button. Okay, so that's effectively our user interface. We do need to make one more change because I want the panel to slide away completely. So in the on create, navigation pane options, there is a collapse for it. I'm just going to set it to 0. So when we run that, that shows and hides our navigation panel. That is effectively our user interface. Let's save that project off. Let's go for ADUG. So I'm going to create a new unit, and I'm going to call it Mandelbrot. So the name Mandelbrot comes from the guy originally sort of made fractals sort of famous, so to speak, was a guy called Benoit Mandelbrot, and I forget where he worked, because MIT or something like that, and he generated some of the first images. I'm going to start with a complex number. It is a record. Now, complex numbers have real and imaginary parts, just like life. Okay, so obviously, yeah. I was worried that was going to die, but that joke. So there's our two axes for our complex plane, which is our real and imaginary, and we need three functions on complex numbers. So we need to be able to add a complex number. We need to square it. And we need to know the absolute value. Now, normally you do this with unit testing and what have you, and a class like this lends itself very nicely to unit testing. But the absolute value is, if you look at our complex plane, a point on the complex plane, it's the distance from the origin. So basically we're forming a right-angled triangle, so it's a squared plus b squared equals c squared, or in our case, the square root of a squared plus b squared. But square roots are a difficult mathematical operation to do, so we're not going to do it because we're calling this lots. And we're just going to square the two. So and we'll compare it to the squared value, which is effectively the same. Adding two complex numbers together is very simple. We just add the components. So our real becomes the real plus the real from the C dot. Actually, how many people are reasonably familiar with complex numbers?
It was about 40 years ago.
Yeah, like it's quite a few. So that's our adder function. Now the complicated one is squaring. So r becomes r squared minus I squared.
45 years ago.
Oh yes, sorry. Now there's a keyboard shortcut to do that.
The older people sitting at the back.
Control. How's that?
What's that shortcut?
That is Control numeric plus and Control numeric minus. So there's introduced in a fairly recent version of Delphi, but I think.
Introduced for presenters.
Yeah. Now, because we've modified our R, and we need it for calculating our I, we'll just create a temporary R0. And I becomes 2 times I times I times our original. So that's the extent of the mathematics of complex numbers that we need to know. We need somewhere for storing our fractal, which we call t-mental data, which is an array of integer. So it's a dynamic array of dynamic arrays of integers. And this time we're actually going to create a real object.
Constant, don't you need to take the square root to get the
You do.
value?
But square roots are complicated. They take lots of computational power to calculate in terms of when you're doing millions of them. So rather than taking the square root of it, I'll just compare it to the square of the
Wouldn't you be better off
number.
calling it the absolute square?
You don't have
Yeah. This will become a problem when I copy and paste some code a bit later on.
to. So, will this
Absolute
just-
square.
Will this just make the colours different?
It will adjust the fractal slightly, but aesthetically it will be the same. So I'm just going to make most of this stuff public. So we need our data. Okay, so we'll just set our self.width. And we need to initialize our array. So it's our multi-dimensional array that's now actually got some space for us to store things. And we're going to need to initialize a whole bunch of other values. Now, a few more parameters we need. It makes some iterations. This is our approximation of infinity. And our bailout value. Both of which I'm going to make integer. And we need to set the corners of the extent of our fractal, so this top left corner and top bottom right hand corner. And that'll be a complex number. Okay, I think that's all we need. We'll find out shortly. So let's okay, 1024, nice sort of round number in terms of powers of 2, and bailout. I think it's really above about 4 or so, or in our case 4 squared, but we're about 8 squared. And so if we come back here, we see we're going to go minus 2.5 and go up to 1.5. So we're just doing plus and minus 1.5 on the imaginary scale, and from actually out here, minus 2.5 to 1 out here. And I think the aspect ratio is approximately correct with that. Okay. We now need to be able to calculate our fractal. So basically, we need to iterate over every single pixel in our array. So that's fairly simple. That's just a couple of for loops. For y is assigned 0 to up minus 1. Now I'm going to write a calculate pixel function. So our data is we're going to calculate based on our xy. So we need to write our calculate pixel, which can in fact be private or protected or and it's going to return us the number of iterations that was required to calculate that pixel. Okay. I'm just going to initialize result to 1. and then while, and it's going to need Z and C, or Z0, no complex numbers. So C is going to whatever Z is initially, and Z, I don't know yet, we'll sort that out. But as we iterate over our formula, remember there are two conditions that we needed to make sure or stay below. The first is the simplest thing to calculate is have we reached the maximum number of iterations we can be bothered doing. So result is less than maximum iterations, and
Got the Cray line you've got there.
thank you. Might be here for a while. And our absolute square, or our is less than the absolute square of our complex number. If you remember our formula, it was z squared plus c. So z squared and increment the number of iterations. Okay, now the only odd thing I'm going to do is if result equals the maximum number of iterations, I can make the result 0. So 0, that is actually inside our fractal. So it's a black area on that image. So the black area in here. Okay, so now we just need to get what Z is, and basically we're doing a coordinate conversion. So we're just doing, we have this pixel to complex, and rather than me memorizing that one, oops, let's just go, and that looks like it. Copy that. Effectively, we are just doing a translation of coordinates. Okay, and in theory, that is all we need to actually calculate our Mandelbrot set initially. And we've written about 100 lines of code, including all the blank lines and what have you. So I'm going to define, on our form, I'm going to define two functions, which are supposed to be private. Procedures. One's called draw fractal. The other is called calculating that draw. Now we need to use our Mandelbrot set and just make sure that that's odd. Already exists. Do I want to replace it? Why does it already exist? And why is it asking me? Did I just say that?
Really what the
Mandelbrot. I think so. Okay. So if this all falls in a big heap, it's all memory currently anyway. So, our calculate is just mean calculate and draw, and we do actually need a Mandelbrot set to do the calculation. And we should create it as well. Okay, so we need to specify the width and height. We're just going to specify yeah. You're going to tell me why this isn't going to compile? So the yeah, that's one reason. So the units in FireMonkey are single precision floating point numbers, and we want integers, so we have to actually round these before we can. Okay, so calculate and draw fractal. Now, draw fractal, I'm not actually going to write because it's actually another annoying things that is slightly more complicated than necessary, but through the magic of copy and paste. Just comment that one out for now. So basically, we are grabbing the image from grabbing the bitmap from the image, making sure the width and height is what we want, and then we have to gain access to be able to write to it. We have to use this map function, and it allows us access to the bit data where we can actually set a pixel. Now, just initially, I'm going to say if data x, y equals 0, then t alpha caloric whack. Otherwise, what? Okay, and if I have typed everything correctly, which I've not done so many times now that why? Okay, and I've done something wrong because that should come back rather quickly. Possibly I have nothing in the calculate. Let's calculate and draw. Main.calculate. Okay, so that's iterating over all the things while. So let's set a breakpoint. And see if we can work out. Result is 1. Z and C.
Bailout greater than absolute square.
And while bailout should be less than if the absolute square. Okay. Okay, there we have a very close approximation of our fractal that I copied off in doing a Google search. So, not as pretty as these ones, but we can solve that, and we're going to do that in some copy and paste as well. First, I'm going to add a couple of units to the project. So, FMX, these color map units. And I'm going to use those units. The other one as well. I don't actually need to, but it's going to give me a warning if I don't. And I'm going to uncomment this, and eliminate that code there. And we need a color map. create it, and we should probably free it to. We should probably free our Mandelbrot set too if we want to avoid memory leaks. At least memory leaks I'll shut down. Okay. So the color map is, this is the FireMonkey version of it, and I have, which contains a sort of platform agnostic version, which is basically just colors. It's an array of colors effectively. So we basically, if get color, if I is 0, so if we're inside the fractal, we return the first color. Otherwise, we return one of the remaining colors, and using mod to map it back. So that, yeah, so you get kind of a gradient which gets wrapped around and around. So our fractal now is slightly more colourful. And we can see sort of the hint of a different colour around the edge. When we implement zooming, that will become a lot more obvious because there are different colours there. Okay, questions so far? Okay, so we now want to start doing some optimizations. And we need to be able to measure our progress. So we want to time how long it takes to generate fractal. So I'm going to use the system diagnostics unit, and in that there is a record called T-stopwatch. So start a new one, and at the end I will stop it, but I don't think I really need to. Just take the elapsed milliseconds. There's actually, if you've used T-stopwatch before, you can actually use it to, there's actually sub-millisecond accuracy if you want really accurate timing, but milliseconds is more than enough for us. And we need to create that in integers will be a good enough approximation. Okay. So we now want to, let's throw a label onto our settings multi-view, and I'll like to align that to top. Actually, everyone else I should use it. Again, our margins, just make it a little bit prettier, give it a name. Calc time. And just give it an initial caption, or text in this case. Calculation time or something. So, calculate a draw. Oops. Quote. Calculation time. Stop to string. Okay, so we're 1.6 seconds, 1.5 seconds. So almost 1.6 seconds. Now, there are some sort of classical optimizations we can make before we start getting into doing stuff on multiple threads and all that kind of thing. which is the fun bit, but it's worth knowing sort of how far we can go without actually making this an incredibly complicated to understand application. The first thing we can do is we can inline a bunch of our functions. So these are called a large number of times, millions of times, basically, some of them. And calculate pixel is called 644 radius, I think 300,000 times. So we'll inline that one as well. Oh, I suppose pixel is complex. We'll inline that too. Oh, and the other thing I might do is in the Form 1 show, or calculate androids, so they have to click on the button every time. Okay, so 1.4.5, so we've knocked off a couple hundred milliseconds by doing that optimization. There is another one that actually gives us quite a bit, and that is to make this parameter a const. So if you don't specify anything, effectively a copy is made of that to make kind of a local variable. We're not changing that at all, so we can pass it as const. And if I go Control-Alt-Shift-E, that will change the definition as well, update it. And we can do similar, although changing these ones actually don't give us very much because these are just integers anyway. So only 4 bytes, whereas the doubles are 8 bytes. We've got 2 of them, so it's a 16-byte structure that we're copying. So we're now down to 1100 odd milliseconds. So we've gone from, with those optimizations, we've gone from about 1.6 seconds, or 1.7 seconds, down to 1100 milliseconds. So it's not too bad. Yes?
Would 64-bit having more registers help?
Okay, good point. So yes, let's try that out. So we'll compile a 64-bit version of our application, and 500 milliseconds. So effectively halved the calculation time, or more than half the application time. So in this case, quite often 64-bit applications are actually slower than their 32-bit equivalent because pointers are twice as large, what have you. But we're actually dealing with 8-byte structures, the floating point numbers. So it actually gives us quite a significant performance boost. So yeah, exactly. 64-bit is quite an improvement.
What if you change the threshold level?
Sorry?
If you just change the threshold level, the visibility.
Yeah, indeed. So I'll come to that when we start zooming in.
Oh, okay.
So in fact, we'll do zooming now. In fact, and I'm going to cheat again and do the copy and paste because you've seen me typing enough code. So there's about 3 functions we need. Let's grab those.
What about range checking and floating point compiler options?
I haven't tested that.
You haven't turned them on?
They're whatever the project defaults are presently.
Yeah.
So I haven't played with those.
Because if you don't have floating point checks turned on, that reduces the code generate.
So that's in here somewhere.
A compiler.
Runtime.
Okay, you don't have overflow checking on. Under runtime errors.
Yeah.
So you got range checking. Okay, well
It's
you've got them off. So.
Okay. It used to be a floating point compatibility thing for FDiv.
I think that was up the top.
But it is kind of.
It should be off. It's pending
There was,
there. So
yeah. So there was an issue Intel manufactured a whole bunch of PDMs, probably millions and millions of them, that didn't do floating point calculations correctly.
Not sure a stack frames would affect this.
But anyhow, so I've written, so there's three functions. Recenter on pixel, which takes our viewport and just shifts it so that the pixel we click on becomes the center, and shrink bounds just takes our viewport and shrinks it a little bit. In this case, zoom pixel 25%. Now I need to shift this and make it public. So they're not. I mean, these are not complicated functions, but to write them, requires, I just have to get a piece of paper and scribble, and it takes me a while to work out how best to do them. But basically, if we go in our on mouse down, so just zoom pixel and calculate and draw. Almost. Ah, okay. You think after writing this 10 or 20 times, I'd remember that. But now we can click somewhere and zoom in. And so we get this self-similarity going on. And as I zoom in, it gets harder, takes longer and longer. Particularly the black areas, because they're reaching our value of 1024. And you'll see how these aren't nice perfect circles anymore. So they're kind of bleeding out a little bit. And I'll just zoom in a little bit more. That's because our maximum number of iterations is no longer large enough. We could add an edit box for it, but because we are playing in the IDE, if I just, let's just set a breakpoint there and do calculate. Grab our bailout value, just throw in the watches. No, maximum iterations, sorry. And modify that. Modify. And then go run. That's taking longer to generate, and there we go. And you'll see that everything's more defined again around the edges. And basically, the more we zoom in, the more the number of iterations we have to do. Now I'll just keep zooming. In fact, let's go out into an area that's going to be the fastest to calculate. So we're going to avoid areas with black. So at some point, we're going to run out of precision on our floating point numbers, and this is going to become more pixelated. But as you can see, we've zoomed in quite substantially, and it's still quite good. And basically, we're getting to a point where if we want to zoom further, we have to write our own floating point number implementation, which I've actually never done. I've calculated fractals using integer math, and lots of sort of shift operations and stuff like that to make it nice and fast. But I've never written a floating point unit. And starting to look. Here we go. So as you can see, we've now reached the limit of our 8 bytes of double precision floating point numbers. In 32-bit, I think we could actually set it to extended, and you can get a little bit further. But I don't think extended is supported on 64-bit.
Don't know why.
I think it's just an optimization thing, because you can fit.
10 bytes, isn't it?
Yeah, it's 10 bytes, yeah.
Ah,
Rather than 8, which you can fit in a single register.
yeah.
Okay. So, one thing I'm going to do is just going to throw an animation indicator on and set it bottom right and enable it. So we can see that our user interface is being responsive at the moment, but when I do the calculation, it's it's stalling. If I zoom in here, I can't move, try and move the title bar around, stuff like that. So the UI basically freezes when we're doing our calculation, which we'll come back to shortly, because first, our next big optimization is parallel programming, which sounds like it might be complicated, but just add the system.threading unit, and so rather than a regular for loop, there's tparallel.for, which has a number of overloads. And you don't actually need the ampersand there. But the one we're interested in is takes 4 parameters. One is the stride length, which we'll come back to shortly. The next is our lower bound, which is 0, and our upper bound, which is height minus 1. And then it takes an anonymous method. Integer. I don't even know where to put these anonymous methods to put the bracket lining up with the procedure or on the end of the end, or. But anyway, so we don't need this that for anymore. And it's going to grizzle at us that y, because the x needs to be local. Oops. And we should have looked how long, was it 500 milliseconds, something like that? 64-bit? It was 490, yeah. So, if I've written that correctly, which it looks like I have, 395, 306. So that's kind of the same, wasn't it?
No, it's about 500.
About 500? Okay. So that's because there is another optimization we need to make, and that's the stride length. So this parallel for loop basically takes our for loop, and at the moment our stride length is 1. So for each iteration over the for loop, it's grouping them in as units of 1. So it creates a new thread for each I, so to speak, or each Y in our case. If I make this 10, it takes 10 values. So it hands off to the first thread, Y equals 0 to 9, and the second thread gets 10 to 19, and so on. So it's breaking down the for loop into chunks rather than individual pieces. And so we're down to sort of 220 milliseconds to do that calculation.
How many CPUs have you got?
So yeah, good point. This is an i5. So there's effectively 4. So there's one physical CPU, 2 physical cores, and 4 logical cores.
Oh, that's fair enough.
So 2 hyper-threaded cores. I used to have an i7, but it died. So CPU failure, actually. So strangely, maybe I was overheating it. I don't know. So we've now reached kind of the limit that we can optimize without rewriting things and unraveling and all sorts of doing weird optimizations to make our code look completely not like anything readable. Or rewrite integer math or something like that, which is I have done. It's not fun. But it's now pretty quick. The thing optimization we now want to make is improving the user experience. So we want to get rid of this kind of freezing of the UI as it calculates the fractal. So we've broken our calculation up into multiple threads. We now want to shift the whole calculation into a separate thread. So the UI stays responsive and the actual calculation is done in the background. Now, to do that,
Sorry, Alister.
Yeah.
I missed that. What did we just get done in the background? If
So,
we didn't do the whole.
it's still being the parallel for loop
Yeah.
still executing in the main thread. So it's farming off all the work
okay.
into background threads, but it's still freezing the main thread.
Yeah.
So while all this calculation is being done in the background, it's not.
Still blocking way.
It's still blocking. And we want to get rid of the blocking aspect. And we're going to do that with a task. So again, we need to use system.threading. And in our calculate and draw function, there's this ttask.run, which is will create for us a new thread and run it in the background. And we're going to use the one that takes a single procedure. Okay, something along those lines. Now, who's going to put up their hand and say, I'm doing something wrong here? What's that? Thread safe. Yes. This is not. So this is now being run in the background, but we're drawing the fractal, which is interacting with the FireMonkey UI, and likewise updating this label. So those things we need to synchronize with the main thread. So basically now when we click this, run will be called, and it'll basically, that procedure will just finish straight away, and this will start executing background thread. So we need to call t3.synchronize. We'll be nice and passing the current thread connection passing nil, I think, quite safely. Yet another anonymous procedure. Okay. So if we do this now, we'll note that our little progress thing, and I should probably try and get them, not have the black near the bottom. There we go. It's not. Okay, there's a little bit of a slight stutter there, but it's pretty much progressing continuously now. So there are still bugs. Because, actually, well, there's two more things I want to resolve. One is the fractal's being calculated in the background. We could actually, now our foreground thread's not doing anything particularly interesting, we could actually have it draw as it's calculating, so we can see the progress of the drawing. So we'll do that next. And let's go through it. A t-timer, and how many times a second do we want to redraw? Good. I'll make it 20 milliseconds, 50 times a second.
Check it out, I can calculate.
Sorry. Draw fractal. I'll calculate and draw. That's, that would be interesting actually, but not necessarily very friendly on the computer. and it's going to not enable it by default. So in our calculator and draw, let's make this visible by, no, sorry, not visible by default. So in theory, the animation should only be visible when we're calculating. Okay, and you can sort of see the effect of the stride length. It's drawing these blocks of 10 pixels. Now, there's still another bug in that it takes a while to calculate the fractal, but I can click as fast as I want. And so we effectively getting multiple threads, multiple versions of the fractal being calculated in separate threads, and then being farmed off into more threads. So what we want to do is when we click to zoom in, we want to cancel the previous fractal from cancel its operation, and then start calculating again on the zoomed in section. And I think that is the last thing I need to do. So,
how about instead waiting till it finishes before you let the user click again?
you could do that, but that's kind of similar to freezing the UI. So you could stop it from doing, but it's not hard to cancel our operation.
So you're going to zoom into the partially rendered one, or zoom in?
Well,
changing the position you're going to...
zoom into the partially rendered.
Yeah,
but it's recalculating from scratch. So
yeah.
I mean, there are optimizations. If I was zooming in, say by a factor of 4, I could reuse some of the pixels from before. So those are Boolean values, and I need to, in the constructor, I need to initialize prefix true, because I've done this in the past. I know that's bad. So so equals false. Cancel because it's false. I do. And this is actually not the best way of doing it, because it does mean there's a bunch of things still going on. So I'm just going to go if cancelled, then exit, and that'll exit our.
Got an extra instruction to operate there. Is it better to do it?
Oh, absolutely. So it'll now take a millionth of a second less.
Well, I was suggesting you put it outside that, please.
I could do, yeah, but it takes time. So we could do it basically at the end of the line. This is not ideal, but it's kind of the easiest and most responsive. And also doing this extra test for every pixel will actually slow it down a fraction. And make it completely true. So I'm just going to define a cancel procedure. Set cancel true, and then while not sleep for 1 second. There is actually a better way of doing this, but I haven't got my head around it yet. Using there's various multi-threaded signaling things you can do.
Complete it.
Compute it. But just, I do need to add sysutils.
Is there a promises thing?
And so when we click, just call cancel. So that'll cancel the current computation, and we'll just kind of busy wait until it's all the threads are finished and all that kind of thing, and then we'll carry on and redo our calculation. So
how you wait using the sleep tool?
okay. It's easy.
Your system's not overloaded.
So basically, I can now kind of zoom in, and I don't have to wait for the fractal to finish drawing. Now, questions? Lachlan?
Did your i7, did it die because you were designing the fractal?
No, I'm not actually sure. I think it's kind of random thing, and I took the hard drive out and put it into an old Latitude, an older one, and I had to re-register Windows, but that was okay. And then I got this one for free, so I pulled the hard drive out again and put it in.
I was just wondering if the time you're doing the fractal for designing a shirt.
Yeah, I was wearing something appropriate. Paisley just kind of got this self-similarity kind of thing going on.
So, what is your frame rate down to now?
So,
if you at the moment it's drawing a screen gradually, which is probably slowing it down. If you switch it up, what is your
let's restart. So we're down to what's 220 milliseconds or something. So a lot.
I think your watches,
for a number of reasons.
The watches aren't probably helping, are they? Because you had
okay.
the watch.
287.
In the debugger.
I would think that would only. Okay. Only from actually paused.
So
yeah.
if there is another mechanism to inform the main thread that I'm done as a thread and I've stopped, right? And we don't need to implement it here, but what would be the method of informing them?
There's a bunch of constructs that are available. I'm actually not a multi-threaded expert, so and hence why the parallel programming library is so awesome that I've written multi-threaded code before for downloading images off a website, so you're downloading 4 or 5 images simultaneously, and it was horrible. That was just unpleasant to write. Doing this with the new T-parallel stuff, it would be so much easier. So
I will warn you, anybody that's playing with parallels and DLLs, I've had a problem with trying to free the DLL with the thread running in the background. It doesn't shut down the way it should.
okay.
It blows up in the case of that. So DLLs, it seems to re-instantiate itself.
Okay. Malcolm.
Sorry, I'm just curious, when you move, I can't remember the exact numbers, when you move the stride length from 1 to 10, I think. And it
What
went
happens?
from 400 down to 200 or something?
Yeah, something like that.
490. 490 down to 200 and something.
What if I made it bigger?
Well, yeah, I'm just wondering, have you played with different ones there to see where the sweet
Yeah, you
spot
can
is?
play it. So that's going to do. There's going to be lots of things depending on. So it's going to depend on how fast the CPU is, and how many cores you've got, and all this kind of stuff. I could optimize it for my machine, but it wouldn't be optimized for
okay.
20
so it's not even
core
just
Xeon
optimized
processor.
for the problem, it's optimized for the hardware as well.
Yeah, so it's a combination. It's a combination because if you've got 8 cores, you can have 8 things going simultaneously, which in my case is 80 pixels. But if you had 20 cores, it'd be 200 pixels going. So
what happens if you do take it up now to...
So yeah, let's throw it up 100. And I've got a couple other things I do want to I can go through.
Because the one thing I don't understand is, like, you just threw 1,000 threads at Windows to say, go manage this. So there has to be overhead.
So
managing
Delphi's doing a lot of the
but at the same time, you've only got a couple cores to run them on, so you'd assume the optimum number would be...
Delphi is only doing, will only execute on as many cores as I've got. And it also recycles, it's got a thread pool, and it recycles the threads so that it optimizes. So there's a lot of internal optimization going into the parallel for loop.
Does it show the task manager that's actually...
Oh yeah, absolutely.
Or even if the thread status in the debugger?
So you didn't actually create 1,000 threads, you created
I'm creating 4 threads.
loops.
1,000, yeah.
And the parallel library decided how many threads to map that on.
Exactly.
In fact, you
That's
even
only-
know that there are 4 threads.
So, I don't actually, no, off the top of my head. Well, if we look at the CPU, let's look at the details tab. No. Performance. And change graph to logical processes. So I've got 4 of them. And if I just start zooming in the black area, we can see that it's it's doing computation all 4 logical CPUs. Okay, so I've plugged my phone in. Sorry, did you?
Yeah, the question I had was, so at the moment the frame rate's been slowed down because you're drawing
Actually,
gradually.
it didn't.
If you switch that off and then...
It actually didn't make too much, like if I... So 600. Okay, so it's possibly doubled or added another 200 milliseconds to the...
So what happens if you switch off that gradual draw and then also run it in run mode instead of debug mode? What's that final frame rate?
So we need to...
Just kill your timer.
Yeah, so don't enable a timer. And that should be all, okay, and run it. Okay, so we're around the 300 millisecond.
And if you switch it to run mode instead of debug?
So that was run mode.
Oh, that would.
And run it with debugging. And considering I've got no breakpoints or anything set, so that's not really much difference.
I thought you were down at 200 at one point.
Yeah.
So you're back up to 100 on the thread pool.
Yeah, what I noticed on some of your early runs
yeah, sorry.
was that when you have that thing
That's-
popped over, it runs quicker the first time without that.
Sorry. So that was setting up this frame length to 100. So we're doing blocks of 100 pixels. The issue there is there's only 480 pixels of height to our fractal. So the first 4 threads, it keeps execute quickly because they all get a block of 100. And then 5th one round, there's only 80 pixels remaining. So only 1 thread gets those last 80 pixels.
So if you do it more like 40 or 50.
So that's why 100 is slower. If we set it back to 10 and run it without debugging, because I don't know if that makes much difference, but we'll do it anyway. Okay, so get back down to 250, 230.
So
Something like 48.
how long before we get to the point where you can run this in real time, zooming in and out?
If I implemented it
10 frames per second.
in integer math, it probably would be able to do it in real time.
So you're at 250 milliseconds there now.
So it's 4 frames a second.
4 frames per second.
To
get to about 16 frames per second, you're getting to something that looks like
almost
real
fluid,
time.
yeah.
What if you double buffered it, like you did all the pixels in memory and then just shove it all out in one go?
Yeah, there's other optimizations that could be made, like when zooming and stuff like that. As I was mentioning earlier, you could reuse some of those pixels.
Now, I found writing to a screen takes a long time, so if you can
And
put
I'm also
that
doing
into a
it.
thread.
What I should be doing is just painting on the form. But I'm using a T-merge with a bitmap and drawing on the bitmap and this then drawing on the screen. That's pretty inefficient as well. So
So if we just waited 2 years and just ran that program, it would get to, with the improvements in hardware, we get to the point where it's real time.
Yep. Yeah.
But you could probably do more things with a GPU rather than CPU.
But then screens will be bigger and so on and so on. I mean
So we need to bring it back in a couple of years. And,
possibly.
And just say the presentation is just press the run button.
Okay. So in the last 12 minutes or so, I wrote this in FireMonkey. So I've got my phone plugged in, and Then it'll come up, and I'll probably need to uninstall, what do you call it? Classical Fractal. So let's just uninstall that one because it's a different version in that page. Uninstall, yes. So, let's see what it's found. It has indeed found my phone. So, we can run this on Android. And eventually it'll come out. So this is one of the really nice things about doing this stuff in Delphi is that deploying to Android is slow no matter what platform you're doing it on. Being able to test in Windows and just compile basically instantly it's compiled is really nice rather than having compile it and deploy it and all that kind of thing. So it's quite nice.
I was developing like a just library for my code, and when I was depending on some native Android stuff, and so I wanted to test the Android code I was writing, but I could just compile the library code without, and it would just build a .so file, and I wouldn't worry about deploying it.
Okay.
I've done that quite quick, and then.
Okay. There we go.
And now we know your phone password as well.
Yeah, indeed, everyone. And so, or I can tap with my finger, and it's doing the wrong space because it's, let's restart it. Best way to do that. Just kill it. No, let's go Fractal ADUG. Okay, it's kind of stretched. The other thing is there are 3 or 9 physical pixels per logical pixel. So actually, the resolution of the phone is it could be calculated as a higher resolution basically, but tap to zoom in, and the latency is quite high on the screen. But I haven't had to do anything. It's a multi-threaded application running on Android. Now, the other thing that I wanted to do.
So what's the speed?
Okay. Oh, did I not anchor that properly? Is that top left? Okay. So no, I can't tell what the. I might be able to swipe from the. There we go. Cool. So that one is 393 milliseconds, but.
Yeah, we can't see
the
it.
screen on the phone.
Sorry. I can't see the screen. Of course you can. I can see the screen. Okay, so 857 milliseconds. Clearly, I have not updated my UI to work. Now, the other thing I wanted to demonstrate, which I just, I've tried to squeeze in quite a lot, was that my phone is nowhere near as fast as my laptop. What I could do is, from my phone, using app tethering, say to my laptop, go calculate this rate for me and return it. And I've got a very basic implementation of that, but it turned out to be quite hard. More challenging than I expected. Even so, the app tethering is pretty awesome. There's some interesting things about it, like when you are sending messages, it doesn't actually let you know who sent that message to you from. It's kind of a weird. So if you send hello from one application to another, the application receiving the hello, there's no indication as to where that came from, and what you can do is actually within the messaging code who sent it, and that's how you get around it. So it's not difficult. It took me a wee while thinking how to solve it. So that's pretty much.
Wouldn't the overhead, if you were sending it back to the PC, be of the order of magnitude of the calculation time?
Yes. So network latency is going to really kill your performance. But if I was doing animations, I could have a rendering farm, and then I could say, you're into this frame, you're into that frame, you're into, and so on. Yeah. And that way.
Buy Cray.
We could buy a Cray, and it would take a lot longer.
What about CUDA doing the stuff using the GPU?
Yeah. So that's something I actually wouldn't mind investigating. I did a bit of research, and I don't think anyone has actually done it, or at least blogged about it or anything like that. So, but I'm not very familiar with CUDA, but it's complicated in that you have to do a whole lot of operations in parallel. The same operation on a whole bunch of pixels at the same time, which you can kind of do, but they'll have to work out. So either using CUDA or OpenCL, that'd be really
What's available? Both are usable from FireMonkey?
I think there is a wrap around OpenCL. Do you know about that? Okay. So you can, yeah, but I have no idea how it works. So
Theoretically, to get 1 millisecond rendering.
you'd get really fast, theoretically, yeah. But the GPUs are not general purpose. The graphics processing unit's not general purpose unit. Yeah, there might be a whole lot of restrictions on what you can do.
Yeah.
So we're in question mode right now. We've got about 5 minutes of questions. So if anybody wants to pepper around with questions.
Or it could be unrelated to the current talk. Yeah.
Could you please show once more how you managed to get this cancelled into the mandable class from outside?
Yeah. So basically, all I'm doing in calculate and draw, I'm just calling mandel.cancel. Okay. And in mandel.cancel, it just says cancel to true and just waits until the fractal is completed in this horrible busy loop. And so in our calculate, we start with completed being false. And if cancelled is true, we just call exit, and that exits out of the procedure. It's still going to get executed a number of times, so this is ideal, but it'll be pretty quick. And then completed is true, and the cancel will finish, and then we carry on with, oops, get back there. Then we carry on with the rest of our.
It'd be nice to have a stop on your sleep to not sleep more than 1,000 times or something like that.
Yeah. There, as I said, there are much better signaling mechanisms. I'm just.
But even if you're doing the evil art nasty thing, if your thread goes feral, you don't want your application, and for some reason crashes.
Yep.
Your application is dead.
Yeah, it's not ideal, but it's 3 lines of code. So
I just like putting timers on.
Does task.run have some other parameters, like another?
Yeah,
it might have a routine. It runs on completion or something like that.
There is. It's 4 of them.
Okay, and you got future.
Yeah, there's a whole bunch of.
Wait for any is the answer. The wait for the ones below them.
Wait for any.
Yeah.
Yeah.
You just need. The trouble is, then you need to track it. You need to create an instance of your task, which you then track around all over the place.
Yeah. Yeah. This is. I've had the last couple of weeks have been interesting for me, so I've not actually had to spend as much time as I wanted to. Looking at this.
Run returns an iTask.
Yes.
Yes. That's what I mean.
Yeah.
But you have to track. You have to.
Yeah. You could
have it run from where you were to where you are.
Yeah. I could then pass that task into the fractal.
What's iTask? Can you just fill that in? Oh, check cancel.
Yeah, there might. There's a procedure. Yeah, I don't, maybe I can take advantage of some of those. They might not actually do what we think they do. They might actually just set a flag or something. So I think there's a cancel on T-thread as well, which doesn't do what you think it does.
Alister, is your program available?
It's on. In theory, it's on the memory stick. I haven't tested the one on the memory stick though. But this presentation I'll put onto YouTube, so you'll be able to watch it, and I'll make source code available for it as well. Actually, I could, like in the last 2 minutes, if I can find it. Fractal with tethering. So I've got this calculate remote in it. And since this basically sends a message to calculate a fractal, and in the tethering resource received, it calculates a fractal, the fractal based on the parameters that are for that fractal, and then it sends a message back to that of the fractal, sends a stream. So it puts that fractal into a memory stream and then passes that stream back to the original caller. When that is received, basically just copies the data.
So we get a copy of that code as well?
I can make it available, yeah. It needs to be tidied up because it's pretty horrible and you can't actually tell if it's actually done anything.
Okay, so if we're going to have a follow-up email for all attendees. It will have links to a couple of different download locations, one provided by ADUG, and also each presenter might have a separate landing page as well. So, Alister, thank you. So, leading up, we've got lunch coming up